Right, hello. Just want to talk briefly about the practical work for the GCSE in Astronomy. Just give a few hints. I'll probably be making a reference to this particular project I've got indicated by this diagram. It's not actually a GCSE astronomy project, but it has a few points which will hopefully be useful. You can see what they're trying to do. Well, maybe you might be able to guess what they're doing here. What they're actually show it a bit clear. What the suggestion here is that you look at a star disappearing behind a chimney every night, note the time, and that will allow you to calculate the sidereal day. I mean, obviously, this was just a suggestion. Students could come up with their own ideas on this. Just to go off the tangent for a moment, when I talk about the sidereal day, it's primarily sidereal means with respect to the stars, but really we're talking about inherent periods. You know, the sidereal day. Well, I should say that you've got this sort of fictional idea of a celestial sphere upon which all the stars are fixed, and to a very good first approximation, the stars do not move relative to each other. So when you're detecting a star going behind a chimney, what's actually happening is that the entire celestial sphere has moved around once. So that's what you're superficially recording, but actually what's happening in reality is that the Earth itself has moved around its axis completely once. That's what you're measuring. The more usual sort of solar day that we tend to use on a day-to-day basis, that's a different thing in so far as it needs to take into account that the Earth is moving around on its own orbit as well. So, you know, if for example, you're going to denote a solar day as from noon to noon, then that will be 24 hours, slightly longer, because precisely because the Earth has moved on its own orbit around the Sun during this particular one day. But the sidereal day is the inherent time that the Earth has taken to rotate about its own axis. Likewise, the sidereal month is the time taken for the Moon to go around its own orbit around the Earth and come back to where it started from. Again, the synodical month is something that needs to take into account the Earth's own movement along its own orbit, and that's obviously a couple of days longer than the sidereal month. At the same time, the sidereal period, when you're talking about, say, for the planets, it's the same idea. It's an inherent, period. So, say for Neptune, the sidereal period is 165 years. So you could detect that on the sidereal celestial globe, I should say. It'll take 165 years to go around the celestial sphere, but what that's showing is that's the inherent period. That's the time that Neptune takes to circle or to go around its own orbit around the Sun once. To get back to the project, the practicalities of the project, if you're setting up, if you're measuring this particular star, then one thing that is not going to happen is the star is not going to disappear instantaneously. There will be a period when it's bobbing in and out of view because your head's moving or your eyes are moving and so on. And that's what you should measure. You should measure when it starts to go out of view and when it finally disappears. That would be the uncertainty. I mean, on this particular project, if you can see this, this was just some general notes that were accompanying the project I've just been talking about. And you see on there they say plus or minus 2 minutes. And what actually happened was that one or two students, when they were handing this project in, or their attempts, they would also put down plus or minus 2 minutes, which to my mind implies that they've missed the entire point of the exercise. The uncertainty, that was just for explanation purposes. The actual uncertainty is something that you should measure yourself, and it's not immediately obvious how this uncertainty will vary. You know, I mean, as I said, it's very, very unlikely that it'll be 2 minutes, as stated there. And one thing you can be certain of is if it should ever be 2 minutes, or if it should ever be plus or minus 2 minutes, then the chances of it being plus or minus 2 minutes on any other occasion is practically zero. The random errors or the uncertainties and so on, they just don't occur as regularly as that. What should I say about this? I mean, there is a very boring exercise that is sometimes recommended where you sort of split a class up into two. Half the class tosses a coin and records the head and tails sequence that they're observing, and the other half attempts to write down a sequence just from how they think a sequence would be. And then at the end of the day, they compare and they realise that there are great differences between the real life sequence and the sequence that they've just made up. It's not just obviously that the figures are different. It's just that there are longer sequences of, say, tails than you might imagine, and all this type of thing. I mean, according to an early pioneer of statistics, Jacques Bernoulli, he defines statistics as being a topic that opposes our intuition. So, I mean, the point really I'm trying to make is that just try and be as honest as possible when you're recording these uncertainties. I mean, if you try and make them up, then there's always a possibility that a professional statistician could come along and realise that you have just made them up. I mean, just record the uncertainties as honestly as you can, and then you're in. That's all we can ask, basically. I mean, I might sort of hammer this home, but possibly by stating that I'm led to believe that some projects, these may be just projects that involve a lot of readings, but some projects I'm led to believe arouse suspicion because they don't have any errors which are really massive. I mean, if you're taking a large number of readings, then you expect one or two readings that so largely out of order that they just can't be true. That's just the type of thing that happens in real life experimentation. So that's probably not so relevant here, where you're taking a comparatively small number of readings, but it's just pressing the point home. So really, I mean, the point of this projects, well, the point of this project, and also possibly any other project or most other projects you're going to try, is it's not so much to get to derive an accurate figure for the sidereal day, because basically you know that already. The sidereal day is approximately 23 hours and 56 minutes. So you're not really trying to derive that. What you're really trying to say is, this project, is it really robust enough, or is it accurate enough to produce an accurate value for the sidereal day? That's what you're really trying to test, which is something different, really. I mean, again, this is a notoriously inaccurate experiment. This is called Fletcher's trolley, and this is attempts to find g, the acceleration due to gravity. You've got a weight here which can vary. You can stick weights into here which can vary, and so on. And you just let the thing go, and you measure the time, and from this you measure g. But the point is that if you do this experiment and you get a g which is very close to 9.8 meters per second, then there is a great suspicion that you fiddled the experiment, or you fiddle your results, because it's a notoriously inaccurate experiment. I mean, I've seen a situation where someone was addressing this, saying, "Is this an inaccurate way of detecting G?" And what they did then was they took the trolley, slung it up with strings, and set it up as a pendulum with this bit as the palm, as the bob. Then they set it in swing, measured the times of the swing, and therefore thus measured G, which in fact in that particular situation was accurate. But the point they're trying to say is that normally this is quite inaccurate. So as I say, it's the same thing. I mean, if you're to do that in the normal way, fiddling around with weights and measuring the time of travel and so on, you would be answering a question, something along the lines of, is this an accurate method of measuring G? To which you would probably say no. And as long as you've done your experiments fairly rigorously and so on, and one thing and another, then that would be perfectly acceptable. You've got the question, is this an accurate method? And you've just said no, and you're able to produce some evidence to support your ideas. It's a bit like in some detective series. Sometimes they say, they come up with a negative result, but they say, okay, a negative result can still be a result. It still has its uses in a way. The thing is that in my own experience, if you take this a bit more seriously, if you check the timing mechanism, there's normally a fairly primitive method of timing this. If you check the timing mechanism is correct, and you try and reduce friction, and you look at it and you reduce friction, or you consider friction properly, and you set up another equation which has friction in it, because some people treat friction here as a bit in a lackadaisical way. That's possibly one of the errors that can creep into an experiment like this. But if you treat it seriously and you add another equation, it obviously becomes more difficult, and so on. But in my experience, you can produce a more accurate figure than is normally expected. But the point is, if you do that, then you do need to put it in your method, what you've done. You can't just say, okay, I've produced an accurate figure for this. You need to put it in your method so that other people can follow your method and actually prove that you're right, and prove that your conclusions are correct. So yeah, what I'm stressing here is that the errors and so on, the uncertainties, that are part and parcel of the project, really. If there's any chance of any errors creeping in, and you can probably go on forever thinking about this. A lot of these projects are quite open-ended, So for example, you could think, okay, if you've got your measurement, say, for a particular day. Typically people would say, okay, it starts at a particular time and ends at a particular time, and I'll take the reading right in the middle. And you might think, okay, is that justified? For example, how do you measure when stars finally vanish completely? Do you hang on for about 5 seconds and say, okay, it's finished? In which case, there might be cause for concern as to whether the actual real sort of figure that you're going to record is actually in the centre. You might have a sort of different uncertainty one way than the other. I'm not saying that that could be the case, but I'm just trying to sort of give you a clue as to things you might be thinking of. So a typical submission, if I was to do this, this might diverge slightly from a GCSE example, but you might put down an abstract, because in real life, if people are skipping through lots of papers, they want to see a paper that attracts them, but at the same time the explanation is quite short. So there is a sort of art there in bringing these two contradictory ideas together. After that, you need to put down the theory. That's for anyone who's caught by the abstract. So the theory for this particular one would involve this explanation of the sidereal day and the synodical day, or the solar day, or whatever you want to call it. You're then stuck in another section for the method. So essentially that's what I covered already, really. You need to put the method in for the benefit of other people. When I was dealing with this in real life, a lot of, or quite a few students put down things like they were saying, I was doing this about 11 o'clock at night, and some people were going past and they thought, looking at me quite suspiciously and all this type of thing. But we don't want to know that. The method is not the history of the person who's actually, it's not a history of the experimenter's own personal experiences. It is there for the purpose of someone else who can then follow your method and sort of certify that what you've done is correct. You then put down your results, which, as I said before, just put them down honestly, and then you can sort of analyse your results. And again, there's all kinds of things you could think about there. And I mean, typically you could have a graph, but I mean, if there's a sort of straight line, if you know there's going to be a straight line relationship between what you're measuring in a particular experiment, one thing you do not expect is that you can draw a graph and all your points are going to be on exactly a straight line. Again, if they are exactly on a straight line, that's going to arouse suspicion. The best you can hope for is that they're going to be not too much not too greatly scattered, such that you can actually sort of draw a good straight line through them, and hopefully make a claim that there is a straight line relationship. Maybe, I mean, other relationships exist apart from straight line equations. So rather than straight line relationships. So I mean, the points could be scattered a lot more complicated than that necessarily, possibly, depending on what on the particular project. So yeah, again, it's quite open-ended here. There might be other things you can think about saying, and so on and so on and so on. And then you can put a conclusion at the end. Again, typically for this, it would be a short conclusion as to whether this is a good experiment for measuring what you're trying to measure. And if not, why not, and so on, and ways you might be able to improve the experiment if you had another go, and so on, things like that. So yeah, that's really the main points that I wanted to cover. So I mean, as I say, these projects vary a lot. I mean, I can't sort of give hard and fast rules for all of them. I mean, there's experiments involving a sundial or similar things like rods in a shadow rods and things like that. And sometimes people are reluctant to do this particular experiment a couple of times. But I mean, hopefully I've been able to put across the idea of the way that errors do crop into these things. I mean, for example, if you were to do the shadow rod thing or a sundial, and you've got a graph out like this, your points might have been roughly in a curve, so you might be able to draw roughly a graph like that, and you're interested in that point there as registering sort of noon, if you like. The thing is, you would have been taking the readings fairly regularly, so that this graph would be fairly fairly accurate. But this particular point here, you're very, very unlikely to have actually recorded it at this point, and if so, you wouldn't not necessarily recognise anyway. I mean, you might know the local noon from some sort of instrumentation, but I mean, you're not to know how accurate your own sort of shadow rod thing or sundial is. So you're either, this point here is subject to some sort of error, because you might have taken a reading here and so on. So you've sort of approximated the maximum point. And how much is that likely to be in error? Well, again, you can only really tell by doing the whole thing again. And depending on if you do this, what sort of result you get when you do it a second time, you might feel like doing it again. It's very, very open-ended. In general, I mean, I know it might be on this particular experiment, it might be hassle doing it repeated times, but the more results you can get, the more confidence you've got in the actual results you're getting out. I think you definitely need to do an experiment of this type more than once. I mean, in general, you might think, okay, you're getting a small error, but if you were to do this in practice, if you're, say, on a ship trying to use this type of thing, detecting the sun at noon to detect your latitude, a small error could still amount to a considerable error in distance, if that's what you're trying to calculate. I mean, an actual error of 1 degree, if you're going to do this to calculate your distance on Earth, an error of 1 degree would amount to about 100 kilometers in distance. And the reason you can do this fairly straightforwardly by in your head actually, you've realised that the circumference of the Earth is 40,000 kilometres. I mean, this was defined, when the metric system was being set up at the time of the French Revolution. They determined that the circumference of the Earth was going to be 40,000 kilometres, and obviously that's very close to the present day figure. So the error per degree will be something like that. So using the sort of approximation that you would tend to use at GCSE level, GCSE maths level, you could approximate that by saying something like that, and that would just go down to 100. You can do that in your head. So you've got a small error in terms of number of degrees, but you've got a large error in terms of kilometres. I don't know, shall I talk about... I could talk briefly, say, for example, about the... well, possibly just to talk about the measuring meteor showers. I could probably just talk briefly about that, just to end it. I mean, I don't want to go on forever and ever trying to cover every single project. I mean, measuring the radiant of a meteor shower, again, this is almost implicit that you're going to have errors in that straight from the word go. So you're going to need to decide on the method and just put that method down for other people. And you're also going to be aware, really, have some awareness of what the errors are going to be. And that's part and parcel of the experiment in itself. And I mean, this could also include things like how you might class something as a sporadic or a real-life meteor, from a particular meteor shower. During any particular meteor shower, not all the meteors you see are actually going to be from the meteor shower itself. Sporadics are ones that would have occurred anyway. So how do you differentiate if there's one which you're not unsure, if there's one which you are unsure of? There's all these kinds of little things you can think about. One thing you could also think about for that is you might consider measuring or recording the timing for all the meteors that you see. It's obviously going to be a bit difficult if it's a major shower. The reason I say that is that the number of meteors you see during a shower does vary. I mean, normally the best time to see a meteor shower is in the early hours, because at that particular time the Earth is actually moving face on right into the cometary dust. So you expect the number of meteors you see to vary from hour to hour, but it's also going to vary on a statistical basis. If you do it for one night, you might not get exactly the same. Well, you're unlikely to get exactly the same results the next night, but next night might possibly vary quite considerably. So I mean, again, that's just another thing you can think about. I mean, I know with the meteor showers, it's going to be a bit difficult to repeat it too often, unless you're going to record different meteor showers, which obviously is going to vary from the radiant, but you might think of something which is common to both, or however many you're going to do. As if, for example, as I've just said, the way that the meteors vary over the course of a night. Yeah, okay, so I think that's probably all I need to say. How much? I've been on for about 25 minutes. I mean, I can't be conclusive on this. There's no hard and fast rules, but hopefully I've given you something to think about. But the one thing that is really necessary to think about as well is the weather. These observations are going to be affected by the weather conditions, so it's best to start any observations sooner rather than the later. Obviously we've well, what can I say? There's always one or two who do leave it too late. But yeah, all I can say is, start it as soon as you can. Anyway, thanks if you're still with me at this stage, and all the best.